This is tutorial 4B Laplace Transform, question 7. In this question, we are given the following differential equations relating output y with x, and then we are asked to find the transfer function, and from the transfer function and from its poles and zero position, determine if the system is stable or not. So basically, we are asked to find the Laplace transform of this differential equation of ys given by some expression equals to xs given by some expression, and then we are asked to find hs is equals to ys over xs, the transfer function. We then plot the poles and zero of this transfer function, and then we can determine from the pole location if it is on the left hand side of the s-plane, then the system is stable. Let's now proceed. To find the transfer function, the first thing to do is that we have to consider only the initial conditions to be 0. Additionally, for each of these d2yt, dt squared, we perform the Laplace transform. This is s squared ys minus s y0 minus y prime 0, because we say that to find h of s, there must be 0 initial condition. It means that these values are equals to 0. The second one is 3 dyt dt. This is 3 sys again minus y0, and again the initial condition is 0, means this guy is 0. And the last one is 2 yt. The Laplace transform is 2ys. We collect all the ys together and we'll get this expression for ys. We leave xs alone. This is the placeholder for the input. The transfer function is defined as ys over xs, therefore it is nothing but 1 over s squared plus 3s plus 2. We will convert it into factorized form, which is s plus 1, s plus 2, and therefore now we see that there are two poles. The pole is at minus 1, because when s is equals to minus 1, this becomes 0. 1 over 0 is infinity. The other pole is at minus 2 for this guy. Again, when s is minus 2, this guy goes to 0. 1 over 0 is infinity. Therefore, the two pole position are at the left hand side plane. Where is the left hand side plane? Real part of s, the imaginary part of s, and we'll draw here a cross to represent the pole which is at minus 1 plus j0. So this is j and this is minus j, and then we will draw another pole at minus 2, so this is at minus 2. So because the poles are all on the left hand side, the region of convergence will draw this dashed line, and we will shade now the region of convergence, which is on the right hand side of the pole nearest to the right hand side pole. Among all the poles, the right hand side pole, the most right pole. We'll draw the region of convergence by finding this pole and shading on the right, because this is a causal signal that we are examining. So if you read the answer carefully, it says that because the poles are at the left hand of the s-plane, so it means it includes the imaginary axis, therefore the system is stable. So that is the key idea. We have looked at the imaginary axis over here, and as long as the region of convergence include the imaginary axis, then the system is stable. The other way we can do is to find the impulse response. So given that we have found the hs, and we can factorize it by partial fraction expansion, individually we can perform inverse Laplace transform to get e minus t for 1 over s plus 1, e minus 2t for 1 over s plus 2, there's a negative in front. This is the h of t. For Bibo stability, the other way to find out is that we will perform, or we will evaluate if the impulse response is absolutely integratable. First, the the time impulse response is causal only on the right hand side ut. So the integration becomes from 0 to infinity. You perform the integration of e minus st and minus e minus 2st, you get this, and you substitute for different values of t. T from 0 to infinity, the answer is 0.5. Since this is finite, therefore it says that the impulse response is absolutely integrable, which also means that this is Bibo stable. But you realize that if by studying only the region of convergence, including the imaginary line, there's a much easier way, but it means exactly the same thing, that the impulse response is absolutely summable. We now focus on part B of the question. The input is unit step. The initial conditions are 0, and we want to determine only the steady state response YSS. So let's try. When input is unit step, the Laplace transform of unit step is 1 over s. Ys is h of s multiplied by 1 over s. So this is 1 over s, which is the input, multiplying by h of s. This is h of s. Remember that the initial condition is 0, so this goes to 0. And now we are going to solve for the partial fraction of only this term. We have 3 rational functions, a over s for this first guy, and in the second guy, 1 over s squared plus 3s plus 2 is broken down into these two parts. By partial fraction expansion, you find a, b, and c. Now we know that the inverse Laplace transform is b e minus 1t, c e minus 2t. As t goes to infinity, this goes to 0 and 0, showing that the only thing interesting is a over s for steady state. Steady state meaning as t goes to infinity, what is the value of yt? So it is simply a. A can be solved, and the answer is a is 0.5. This is the answer to our question. So simply for this question, the answer at steady state is y of output is equals to 0.5. Thank you.